So yeah, my name is Matthew, and I'm going to be presenting this lab today about timeless analysis and timeless debugging. +1 on the Discord chat. It's super important that you guys join the Discord chat as well, since we during this talk we'll have a small contest which allows you to win a couple of licenses. It's important that you can send the answers to the contest through the Discord chat. So if you didn't join, you will not be able to actually participate. I'm not alone. I have a couple of colleagues and I'll present them in due time. And they also will participate. So they follow the Zoom chat, but they will participate in the chat. So if you have technical questions, technical issues as well, you can send them over to them directly, either through the chat or through the DMs, and they will help you out with the material. And yes, Skia just said hi on the chat. Okay, so let's start. I hope you guys are all here. I hope you guys are all well, and I hope you're not too tired because we're kind of reaching the end of the conference. Hopefully we have all your neurons ready to absorb this 2-hour lab about timeless analysis. So my name is Matthew Favreau. I'm going to be your speaker for this lab. I'm an engineer at Tetrane, the software editor of the REVEN software, and REVEN is actually a timeless analysis tool, and we'll actually talk about that a little bit later. I've been involved in development, demo labs, training, that kind of thing at the company, and you can reach out to me either on Twitter or through my professional email, which I reproduced here. And you can reach out to me on Umbrella as well. I know a couple of you have done that already. So that was about me. As I said, I have a couple of colleagues on the back office side, Florent and Quentin. Florent is Skia on the chat, and Quentin is Quentin. They're both identified as Tetrane if you need to. One is a DevOps and the other is an R&D engineer at Tetrane as well. And they've been super helpful on this lab, so I'm definitely not alone in the material I'll present you. They've worked on the VM infrastructure that you're going to use for the lab. They've been doing some proofreading of the exercises. They gave me feedback, and they're going to be supporting the chat today. So hopefully all the questions that you have will be answered either by me orally or by them on the chat as well. Again, if you have questions during the talk, I'm still monitoring the chat on the side, so you can just push them and I'll try to answer them orally if that's possible. So don't hesitate to just pop in the chat and send something else. About the agenda of today, I'll start with a quick intro about timeless, what we call timeless debugging and analysis. There are a couple of names around for that kind of thing, so I think it's good that we kind of define the terminology and what it is about. And so I'll present the various concepts, a couple of very common tools that do that, including our own. And then once that's done, I will start presenting REVEN itself, because since the lab is going to be centered around the timeless analysis usage through REVEN, we need to be familiar with the tool. And since this is what you're going to use for the next 2 hours and you probably have never used it before, I think it's good that I start presenting the tool, the widgets, how it works, how you're supposed to use it. And then once that's done, you have a better understanding of what we have in front of us. Once I did this introduction, I'll give you access to the virtual machine that you can use. Through the chat, I'll send the link that you have to use. In that link, you will have to enter the email address that you use for the registration. Your VMs are already created. They're just waiting for you. And then we'll start working on the exercise themselves. So exercise 1 is going to be a very simple program, short trace, 300K instructions, something like that, and on Windows. And this is going to be for you the introduction to REVEN. You're going to have to reproduce what I did on the screen through the UI, get used to the tool, because working on a trace is something quite different than working in IDA, for instance. So this exercise is going to be the occasion for you to understand the concepts that we are going to manipulate. Again, see the kind of thing you can do and extrapolate how this would work on a bigger trace. Then exercise 2 is more of a real world example. It's actually Bad Neighbor CV. It's a CV in a, it's a crash in the Windows, one of the Windows drivers, when it's handling a badly formed IPv6 ICMP packet. And again, through this exercise, we will focus on what timeless analysis can help you discover about something like that. All right. Finally, exercise 3 is going to be about CV, which I won't name because we'll have this will be the sport for our little contest. And then this exercise is going to be a little more free. I will give you questions to guide you through your analysis, and this will be the questions that you will need to answer to participate in the contest. But the idea here is really to have a freer exercise where you have to, there are much less rails for you to take, and yeah, you're more free. You might get lost in the trace or not, you know, depending on how good the previous exercise were. Hopefully you won't get lost, and you will be able to find, you know, the kind of things, again, reproduce the same steps that you did in previous exercise, but on this new trace here. We have 2 hours and the timing is pretty tight. So we'll see how it goes, and maybe we'll drop things along the way, and I'll just spoil things and just give you the info and move forward, because otherwise we will never reach exercise 3. And I have to make sure that we can reach exercise 3. But for exercise 1, we'll take our time and make sure that you guys have a good grasp of that. I see a question popping in the chat, so I'll move forward. Again, if you have some, don't hesitate. All right, so timeless debugging. Again, there are a couple of names for that, but the principles are all the same. You have something that you recorded, an execution of something, a program, a virtual machine, whatever. You recorded that execution. And then you can look at this execution in the past, that you've done in the past. It's basically frozen. So you can look at every point in time in that execution of something and look at the state of your program, the memory, the registers, maybe the IO, something like that. So that's really, you start recording something at one point. Then something interesting to you happens, and then you stop recording, and that chunk of time you have access to, it's frozen in time, and you can look at it however you want. That's really the gist of timeless debugging. You can step backwards, step forward, just as you want. And there are tools to do that. There are a couple of tools that exist today to do this kind of thing. I'm not going to be doing a comprehensive list here. That's really not the point for me, just to kind of introduce the various approaches that various tools can have. That's really my goal here. So sorry if I'm forgetting a big actor here. That's really not my intention to be comprehensive. Most of you may have heard of WinDebug, however you pronounce that. WinDebug preview, that it calls that time travel debugging. So it's really the usual WinDebug interface, but just you record a program and then you can step backward in it, and you have a couple of indexes created on top of that to help you work. But that's really the WinDebug thing. It's really integrated into Windows. It's something very powerful that you can have in Windows. The sort of equivalent on Linux is going to be Mozilla R. You have a GDB interface that you can connect. It's really integrated with GDB, and you can step backwards, step forward. It's developed by Mozilla, so they use that to debug Firefox mostly, I think. Another tool, an OSS tool, kind of the underdog, is Quera. It's Linux only as well, as far as I know, but I mentioned it because it's really interesting. It presents a view of the trace instead of just a view of a debugger through a UI. So that's interesting because this is something Revan tries to do as well. And these 3 tools are focused on a single process, or at the process level. They won't dive into the kernel or anything. They really are meant to debug a process. And most of the time they work on multi-threads. Then on the other side, you have full system solutions that work on virtual machines instead of a single process. So that's kind of a trade-off. You have more information, but you have more information that you need to filterize. It really depends on the kind of thing you're trying to achieve. Full system solutions include, first of all, Panda, which is a fork of QEMU. It's pretty robust. It allows you to record and replay a trace. there's a C API, so you need to write your own plugin to extract information. There are already existing plugin, a forward taint plugin, this kind of thing, but there is no GUI, no actual GUI that you can use. Again, it's maintained, it's pretty robust, so that's a pretty interesting project. But the approach is really to record and replay the same trace over and over again as you need it. I don't think you can actually step backward as you can in WinDBG. Then you have QEMUR. It's an entry thing, GDB only interface. I have trouble trying to make it work before, so I'm not sure how supported it actually is, but the fact that it's entry is pretty interesting. And finally, full system solutions, there's us, REVEN. So this is the tool we develop. We support multiple recording backends, including Panda and another one based on VirtualBox, these kind of things. But the idea is we try to provide a lot of tools on top of your trace. We provide a GUI that presents you with a view of the trace that we are going to use during this lab, a Python API as well that we are going to use in this lab as well, automated recording, backward taint, forward taint, whole trace memory, things to help you work on a trace, and you'll see why this is so important, why we feel this is so important. And in any case, this is the kind of thing that other tools do. So through REVEN, you will have a pretty good understanding of what having a timeless trace can really give you, whatever tool you choose to use in the end. Yeah, that's what I just mentioned. You get this trace here, but then you get tools on top of it to help you navigate the trace, because in full system thing, traces can be really large, like billions of instructions. So you need tools to navigate these traces. And the data tainting is going to help you connect things in the trace. We'll see all that through the exercises. And maybe I'll come back to this drawing, because it might be useful to have an idea of what we're trying to achieve there. All right. As I said, we are going to need to dive into REVEN, how it works, because this is the tool we're going to use here to illustrate timeless analysis thing. First of all, the first thing I want to show you is how to record a trace somehow, at least the basic steps, because I think it helps really driving the point. We are recording a full virtual machine, and this is going to matter in many ways, not a single process. As I said, different approach. So for instance, here, what I have is, I have a simple virtual machine that I booted up earlier, and I mounted something on the CD-ROM, and that's the file that is on the CD-ROM is actually a proof of concept that's going to crash the OS. So it's not exactly one of the traces that we are going to work on earlier in the exercises, but I think the principles are the same. So here I have one of the UI of REVEN, which is the part that will help you manage your project, record your virtual machine, manage your virtual machine, that kind of thing. And basically what I'm doing is I'm starting the record of the virtual machine. So from now on, whatever I do on the virtual machine is going to be recorded. I made the VM crash to the file, and then I can stop the record. Okay, and then this is what this is the trace of that I will have access to later on if I choose to replay the indexes and everything. So we really record an entire virtual machine running, and then we get access to that. So again, we're not going to work on that trace in particular. I'll explain to you how the traces that we are working on have been recorded earlier. But what do we have here? So I have a trace here. But before we go to that, I'd just like to start very small so we get the concepts right from the start. So I'll do that through the API. Again, the GUI is what you would use to start working on the trace, but I'll start with the API. So never mind exactly what I'm doing through the API. You won't have to reproduce that exactly, just so we get the concepts right. Look at the results, basically. So what I'm doing, I'm going to access the first instruction of the trace. All right, this is the first instruction of the trace. Move something. All right, this is my first instruction. We call that a transition because sometimes there are not instructions. This is basically taking my virtual machine from one state to another by changing a register, changing memory, something. So we call that a transition because in most of the time it's the execution of an instructions. Sometimes it's something a little different. So that's why we have this term transition here. So I have that. But I can iterate on top of that because I have the entire trace. You know, this is not a debugger. I have the entire trace. So I can just iterate and see trace and instruction 3, 4, 5, 6, whatever. I also have access to the entire context at each point of this, trace. So I can display the registers, display the symbols, display memory, whatever. So that's what I'm going to do here. And there's a syntax error. Yep, here we go. And you see I'm displaying some context here, the value of RCX and the value of RSP and the value of memory, which I'm reading here, which contains something. And I can, again, keep iterating on that and get access to everything. Okay. Yeah, I can, so I have access to not only to what is manipulated by the instruction, but to the entire context. So I can just read any register, REP, or I can read any piece of memory, like I can read the stack like this, and you would see the stack moving probably as I move on. Do I have something that moves the stack here? So move, oh, I made a call, all right. So yeah, you see the stack just moved. It's different from what it was. Yeah, basically I have access to everything. Here I call the context I'm accessing is the context before or after. When you have, as I said, a transition, it moves from one context to the other. So you have either the context before that or the context after that. And you'll see that pretty much everywhere in the GUI where we have two contexts for a single transition. That's really how the data is organized. And finally, if I were to print a list of instructions that were executed during my trace, that would look like that, and that's exactly what we have in the GUI, right in the center, right here. That's my execution trace. It's very different from what you have in IDA, because in IDA you basically have all your list of instructions ordered in memory. But here, what we have is the list that was actually executed. So if I have a conditional jump, whether or not I executed it. Depending on whether or not I executed it, the next instruction is going to be either the jump I took or the jump I didn't take. And that's really some different from what you would have in IDA. For instance, here I have an IDA instance that is synced to the view in action. You see it's moving and it's displaying the current action, the current instruction that is selected here. And there, when I take the jump, I'm actually jumping to a certain block. And if you look at this view here, which is the usual view ordered by instruction, I'm actually jumping between these two instructions. So this is really here a list of instructions that we executed. And around that, we have various widgets which represent the state of the machine that we saw, as we saw in the Python API. We have a backtrace. We have the view of registers, again, before and after. So if I see, like here, I'm writing something to RCX, so I see that RCX is changing from 2 to something different. All right. I have other widgets. The frame buffer is really a view of memory, so I can display the state of the frame buffer at that point in time, and that's just video RAM that we show as pixels instead of hex value. So there's nothing special that we record here, just video RAM that we display as an image. You'll see all that during the introduction to the exercise. But yeah, I can also display a view of memory. Like if I double click on an operand here, it's going to show me the operand's value before the instruction got executed. So at that point, if I double click on RCX, it's value 2, so value before, not value after. If a value is an address, you can click on the link and it's going to open that memory view. If it's not, it's just going to try to display an invalid memory, and that's not going to work. So if I double click here, this is the address that I have here, RSP, and that's the content of that address. So I can click here on the address and see the same value, 50, 30, 20 hex in the address I selected. Okay, so that's, again, I have access to the entire context, and you're going to manipulate all that. I told you we create indexes on that trace to have navigation. There are a couple that you're going to use throughout the exercises. The first one is one that is going to make the search very fast in big traces, because you want to be able to, you don't set breakpoints on the trace like that. This is not a debugger. You don't say, I want to see where A to I is executed. You don't set a breakpoint and say, go. What you do is search for a certain call to a symbol that you're interested in, and it's going to show you everywhere that call was made. So I can do that here. I can, use CRT base, and my symbol is going to be A to I because this is relevant to this exercise. So that's my symbol here. Search for it as a single result, and I can go to that result. Well, it was right here. If I had a million results, it would try to display the million results, and I could iterate through each of them, either in the GUI or using the Python API. That would probably be a better idea if I have that many results. So that's how there's no breakpoints really in a trace in Timeless. Or if there are breakpoints, it's really just an interface, a familiar interface for you. Really what you're doing is searching for the execution of something in your database. A quick point here, notice that I had to enter the full path for that binary. That's really something specific to Revan here. There's auto completion, so it's pretty easy to do, but I really need to, by pressing the down arrow or just clicking with the mouse, I really need to select the full path, and that allows me to precisely select which binary I'm interested in, and then look for the symbol, and you see there is auto completion as well if you need it. So that's kind of the equivalent of the breakpoint. And what about the memory breakpoint? Well, the memory breakpoint is in the memory history, in the memory view. We call that the memory history. And by selecting a memory here, any memory region, and clicking here on the show access history, I will have the entire history of accesses on there. And that's really, that could be millions of them. So we center on the previous one by default. And that's really how you would navigate between things. Okay, that way. I can double click on an access and it teleports me at that point in time, and okay. Let me check if I forgot something. I don't think I did so far. And the rest we will see later on. About the exercise that you guys are going to do, the exercises are presented in a Jupyter notebook. So you saw that was a Jupyter, for those of you who are not familiar with Jupyter, Jupyter is a REPL environment for Python. So it allows me to develop Python code, and each cell that you see here share the same Python context. So if I execute that and then that, this is going to be dependent on the result of that. All the exercises are presented through the notebook. So this is the first exercise you see, and there is very little Python for each exercise, but it's still pretty nice to have this view. Because I can do interactive stuff on such a notebook, notably before. And again, I know I'm pushing a lot of information, but it's easier for me to just push all that, and so you get an idea of what you're going to be faced with. You see, every time we talk about transition, there's a link, and if you click on that link, it's going to sync the right action here to that transition. But to do that, you need to make sure this is synchronized. By default, Action is not synchronized on anything. So you see, you need to select default session here. And by clicking on the transition, or that one maybe, you see it just went to 252. Okay, so you're going to need that quite a lot because it allows you to navigate through the exercise. Okay, that's one of the important things I needed to mention. About the exercise, this trace is the recording of a very small program called My Program. It's really a sample. Don't try to make sense of what the program is going to do. It's really just meant to make you use Revan. So what the program does is completely senseless, except for the part that it's going to do things that we can track with Revan. So it takes input from the frame buffer, and I can zoom using control mouse. So that's the state of my virtual machine at the very start of the recording. So I had executed the program twice before I even started recording anything. And yeah, it takes an input and then does something with it. And if you go at the end of the trace, you see that, so I just printed a large enough number to be further than the trace. And at the end of the trace, what we have is divide error. So my program crashes, and we stop the recording just there before anything else happens. So the exercise is going to be trying to, you will be trying to get an understanding of why there is a crash, where the actual bug is, and where the inputs are coming from, and then exercise the various features to navigate that thing, just if it was a real big trace. As you can see, it's pretty small by full system analysis standards. There's 300,000 instructions. Traces can go up to billions of instructions. So that's a pretty small one. You're going to use the various features that we saw to do that. About navigation, so I mentioned hexdump, I mentioned the search. There are two last things I need to mention before I can free you on the exercises. So you see there's a call here, and as we said before, the trace is going to be displaying everything. So what I have here is the first instruction of the call. But what if I just want to skip that call? Then I need a shortcut, which we call %. It's just the person key on your keyboard. And when I press that, it teleports me to the red. Okay, %. And if I press % again, it teleports me back to the call. Okay, so I can navigate. It does that on call, red, on push, pops, on syscall, systhreads, whatever. So that's one thing for navigation. And the second thing is you have arrows here, which help you go back, just like a browser. You can go back to where you were or forward. And that might help you if you just end up somewhere you don't know where you are. You can just use the back or alt left. It works in the browser as well. So this is going to be pretty good for you if you ever get lost. And the same arrows exist here on the hexdump. All right. Let me check. I don't think I forgot anything for this intro. So this is just a gist of what you can do with Revan, how you use Revan, and I'll give you now access to the actual material. Yeah. So let me push a message, okay, to the chat as well. Pin message, there we go. Okay, so use this URL, hitb.tetrane.com/get_email. You will need to fill in the email you use for the registration to the lab. We created the virtual machines already, so they are waiting for you. This virtual machine won't last forever, but they will be available for at least an hour after the lab is over. So if you want more time to explore the traces or anything, we will be available to the chat as well. Even if the Zoom session has stopped, we will still be there so you can keep working on the exercises if you missed anything. Any technical issue, direct message to Skia or Canteen on the chat. They will help you out. And we probably have a couple spare virtual machines. So I see one person said, I didn't sign up. DM Skia if you have any trouble or anything that you need addressing. Let me see, what did I want to say again? So I'll give you guys a minute to get access to your virtual machines. Please add a thumbs up to the message that I pinned. If your access is working, so we can know that everybody is set up and we can start moving forward with the exercise. At least most of the person are set up. Okay, where are we? Okay, 3 people. All right, perfect. So we'll wait we'll wait for some time. Yeah, one person just asking me, how can I get the instance? If you don't have a registration email, we may have a couple of spares. So just ask Skia. He is going to be managing the spares because if I just give you one, you guys might get conflicted on that. Perfect. All right. So while you guys are all setting things up, I think I will give you about 20 minutes to work on the first part of the exercise. On part one, each exercise is split in two different parts. So I will be giving you, I think, about 20 minutes per part, something like that. But I will push a message again on the chat and give a thumbs up to the message where you've done that part. This is really going to help us track everyone's progression. Yeah, this is going to help everyone and help me know that maybe 20 minutes was way too short for you guys to start. And then we'll try to keep, depending on how important that part is, I might give you a little bit more time, or I might just cut short and move forward, give the answers and move forward, because as I said, we have quite a lot to cover, and I already spent the first half hour of the lab talking, and that's really not the point. So let me, advancement. Okay. I'll be using pinned messages quite a lot, so keep an eye on the pin button at the top, which you can use to show all the pin messages that I pushed in order. I'll be making use of that throughout the lab quite a lot. Okay, so here's the message that I was telling you about, and you can just click on the thumbs up arrow whenever you've done part 1.1 of the exercise. Part 1 of the exercise 1. Yeah, don't click so fast. One thing I didn't mention, if you double click on something that is not Python, like I'm doing here, it's showing you the markdown below. You can just Control Enter again, and it's going to help you. It's going to just show the process view again. Just know that, the same way you execute a Python cell, you are going to execute to render the markdown. Here we go. I'll let you the various hints here displayed. A few things I talked about. Activate the session if you want the synchronization and being able to click on the transition numbers. Remember that percent helps you go from call to ret. Double click on an operand is going to show you the state before, and double clicking on a memory is going to show you first the address, then the content of that memory region, which is probably going to be accessed. Alt left and right to navigate, and Control Enter to execute a cell. So 20 minutes, that brings us to 5 to 9 in GMT plus 4. So I'll stop talking for a little while and just ask questions, and I'll address questions that require mentioning orally, so you all get the answers. Yeah, I said part 1, but the part is actually called part 0. So let us know when you finish part 0. And 0.e is optional, and it's about the strings widget, and we are not going to need that throughout the lab, really. So just let me know when you've reached that part, and you can start working on it, but we might get you in the middle of it. And I'll just, give the answers, something like that. So let me know when you've reached the end of part 0.d. That's really what I'm interested in. Sorry about that. Sorry for the misconception. Okay, guys, we've reached 5 to whatever it is in your time zone. I see that only 7 people mentioned that they finished the first part of the exercise. Do you guys need more time, or do you want me to move on? And do you think you've seen the things you wanted to see? We've had a couple of questions on the chat, so maybe I'll use a couple of minutes to already give the answers to the questions that we've had, and then we'll start moving forward. If that's all right. Just let me know. Finish part 0. Okay, so some of you did finish it. Yeah, please leave a thumbs up to the message that I pinned. It's really going to help us out, knowing if everybody is on the same page. About the questions that we've had, no problem about that. Just get used to it. Yeah, so about the question, I wrote a few notes. Yeah, so we do sync with IDA through the WetSync plugin, but we also provide a bridge to WinDebug, which allows WinDebug to connect to a trace as if it were a live running VM, and you can use that as a debugger backend in IDA if you want to. Don't worry too much about the segmentation. It's really in x64, it's barely used anyway. What's most important is the fact that there is a linear, there is a virtual space and a physical space, and you'll see that there might be differences between the two. So that's more important, more relevant to what we're going to do, the difference between virtual address and physical address, which is the actual RAM address that is used by the CPU underneath. Just know that one maps to the other. You don't have to know the details about how it works. And yeah, to open a hex dump, a couple of ways. I showed you that you can double click on an operand. This is the address of the memory. So that's RSP plus 20 hex equals 14 FC 20 hex. And the content of that address is in a keyword is 0. So if I click on that, I'll see that you well, I would like you to click, please. Okay, it doesn't want me to click. Oh, here I am. Yeah, it contained 0 before the instruction was executed, and then it contained that new value because we displayed the state before. And you can also use the CPU registers for that. If you click on, let's say, RCX, what you'll see is RCX. And actually, let me use that. So RCX is the first argument to A to I. In x64, RCX, RDX, R8, R9 are the arguments of a call. So you should have looked at RCX here. So keyword is not a nice way to display that because there's a string there. So let's display that as bytes. And yes, here we are. This is our string, and this is what I passed here as an argument in the CLI to the program's command line interface. And if we show the memory history on that, there are a couple of reads throughout the program. And double-clicking here gives me to the access, and that's just, the A to I call being executed. So I'm passing that string into an integer. And if I go back to the call to go to the red, so I'm double clicking on the call here, I can double click in the backtrace. It gets me to that point, pressing %, looking at RAX, which is the return value. 3B FFD is the hex value of that which we parsed before. Let me look at the point. So that was the memory history. We looked for printf. Printf is not stored in the DLL, but rather in the program. That's really a compilation detail. Don't worry too much about it. Most of the time, the symbols are at the expected place. But we do have a call to printf, so I go to that call, and we can look at the arguments. Again, RCX is the format string. Let me push that upward. Yeah, this one. Let me push that one upward. Like so, you can move your layout around like that to suit what you want to do. So as I said, first argument, second argument is actually the integer, and the second argument, is a string called input, and the second, you can see it using as byte. That's input, and the third argument is the integer. I won't spend too much time on the strings because we really are moving. Time is moving really fast. So if you want more details on that part, we may talk about it after the lab is over on the Discord chat. So you should have seen these things here. And the second part of the exercise is you're going to start doing some timeless actual analysis on top of that, not just debugging, moving forward in the thread, but actual analysis using the tools, the various tools at your disposal. The most important tool is the taint, and we need to talk about it for a second, because the concept is really important, and this is one of the most important navigation tool that you may have in a trace like that, because it really gives you quick answers for things that might not be super easy to get. So some of you might have used tainting engines before, and some of you might have not have used that. So I'll start from the base. Actually, I'll use the exercise. I'll spoil it a little bit. You can manipulate that after by yourself if you want. That's really the point of the exercise here, is really to get used to Revan. So there's nothing to really discover here. It helps me get answers about things. What is the problem I have here? Here I have a value, RSP plus 8. I can't select it because it's not valid. RSP plus 8 equals 0. And I want to know where this 0 value is coming from. So I can look up in the trace and see that this is the same RSP, which is going to be 0 at the end of this instruction. And it comes from RCX. Okay, so now my question is where RCX is coming from. RCX is coming from that value here on the stack. And where is that one coming from? And here RSP changes because I have a ret, so I know I have to compute the offsets in my head, or switch over to IDA because it does a pretty good job on that. So I could head over to IDA and help me out here. And since the code of the program is like super small, this is going to be an easy job. But assume that this is not a simple program. Assume you have tens of embedded calls one into the other, or that data was pushed and moved around. And it's going to be pretty hard for me to track where it's actually coming from. And that's where the tainting engine comes into play. It's going to put a taint on a certain value and propagate that taint either forward or backward to help you either find what is dependent on that value, or what this value is dependent on in backwards. I hope you see me in the proper direction here. So in that case, if I taint the content here, the address here is going to taint the content of that. Backward, it's going to tell me where the value is coming from. It could have moved from a register to a memory to another register. It might even find that maybe at some point, two values have been mixed together to create this new one. So maybe added or multiplied or something like that. Then it will start backward, tainting two different values and give me all these branches and tell me exactly what that piece of data was dependent on. So that's really following the data flow, not the control flow. That's really important. We are only going to be interested in the data flow here, and this is what it's going to do. So how do you use that? You can open up the taint widget here. Again, the exercise is going to guide you through that, so you don't necessarily have to do it on your side. Just watch me doing it, and I'll give you an idea of how it's going to work, and then hopefully the exercise can take over. So that's my tainting widget. I can place a tag. So the tag is the name of my taint. Usually we just use tag 0. Don't really worry about that. So in that case, I can taint, say, RCX, type it by hand, and then I need to specify from the starting point of my taint and the ending point of my taint. So I'll say just taint it from here, the current transition that is selected here, and then backwards, so up to the first transition. This is a backward taint, and selecting to the last would be a forward taint. But in my case, I want to see where it's coming from. So I want to do a backward taint. I'll move my way backward, and then press taint. Okay, notice that I placed RCX, but I could have used this memory region instead. So I right-click, copy current address range, and then paste that into that field. Okay, and it's going to taint that region from the state before. So that's a slightly confusing thing. It's going to start tainting the state before the instruction. So in my case, I need to move down a notch. So I had the actual 0 in the before state. This is what I want to taint. And then, so yeah, current transition again, and I can taint that, and I will have the same results. Basically, it's going to say me, yeah, it's going from RCX, and from that point on, this is the same taint, because at that point, RCX is tainted. What I have here in this widget is the moments in the transition, so the moments in time where the taint was moved from one place to another. or something was gained, so something gained that taint, or something lost that taint because it was overwritten with something completely irrelevant to my taint. So in that case, I see that at that transition, double-clicking here, that transition, I don't have the taint on that memory anymore because it was something completely unrelated, but RCX gets tainted. Yeah, so that's it. And then double-clicking here, again, pretty easy to see, but on a huge program, it makes sense. RCX comes from that memory region, and I don't care about the content of RCX further on. So RCX loses the taint, and memory gains it. And moving your way through the taint result, you'll be able to see quite a lot, actually, and where the value is coming from. One important thing to note is that what we display here are only when a taint has been gained or lost. But if something is tainted and is being modified, like you multiply it by 3, and 3 is a static value in your program, so there's nothing to taint. You can't taint the 3 because it's a value in your program. We won't display that here. You can access that information through the API, but not through the GUI here. So if you see that at some point, something gets shifted left or right or whatever, this won't be shown here, and you need to find it. But usually these kind of things are pretty easy to see in the trace because they're pretty close. So what you see here are the movements, and then you need to, it gives you the list of places where you have to take a closer look, basically. Okay, so I wanted you to see that moving before you had to actually use it, and that's really what you're going to be doing here. The first thing you're going to be doing here is try to determine where that 0 is coming from and how it was built, basically. The other thing is that we're going to be doing here we're going to search for a value throughout the trace. And in a debugger, you might be used to searching a value in the memory region. And what we'll do is slightly different. We're going to search for a value that we're interested in, but throughout all the axes of the trace. So instead of looking at a huge memory region, we'll just look at all the regions that were accessed during the trace. So it's a much smaller scope and very defined. And it makes a lot of sense oftentimes because you're going to just be interested in what the program did, what the program manipulated, and not something that was there and never touched. So we're going to use that as well. And that's not accessible in the GUI, that's accessible in the Python API. But just by executing the cells, you'll be able to leverage that. The cells in the exercise, you can't run them. There's a compilation error because you need to fill in things. So the first cell works because it's going to connect to your trace and do the imports that you need. You don't necessarily need to care too much about that. But the second part, Control Enter, it doesn't work because you need to fill a couple of things. So just look at the code, try to understand what it does, fill in the value which makes sense to what you're trying to query, and then you can use that result. And we'll see exactly what and I'll just give the answers in a couple of minutes as well. All right, so again, oh my God, we'll never have time for the second exercise, don't we? Are we? Okay, so try to do that, and again, take a couple of minutes. We'll take maybe about 20 minutes as well for that exercise. So at 30 past, we'll stop, and then maybe it's going to be time for exercise 3. I'll take a minute and think about it. In the meantime, let us know when you finish part 1 so we can move forward. I'll just push on a new message for that. Let me copy that over. Okay, it's been about 20 minutes since we started the second part of the exercise. So I'll debrief the exercise. As I said in the chat, then we'll start the contest before the exercise number 2. And for those of you who are interested, we'll keep the Zoom session open and we'll stay in the chat for another hour after the end of the lab so we can look at exercise 2 at that time. If you're interested, you can stay a little while longer. Obviously, 2 hours was a short for everything we had planned. About exercise 1, so you should have tainted that value backwards and look at things. Basically, what you should have discovered, looking at the results, at that point you see that we are tainting RCX just byte 0 to 1. That's where is it? Okay. Here it is. where am I? BFFD, and then RCX is here. And then we get that. And yeah, that's because here we're just taking the lower part of the EAX register. So as you can see, we do a couple of things. We multiply it by 4 and add something, and then we truncate that value and just take the lower 16 bytes. And that's actually the reason why there is a 0 value that we divide. So that, as usual, as I said before, here the code is very small, but using the taint might have helped you find that code location in the first place and help you analyze it. One interesting tidbit about the taint at that point is you can display the taint state here. So at any transition, you can display what is currently tainted. And you can see that at the very start of it, the taint tells you that there is this memory region that is tainted. If you click on it, you can display it, and that's my initial string. So just by using the taint, and that's actually centered on just the bytes of the string, not even the 0 to close the string. So here the taint was absolutely capable of just taking your 0 and saying, hey, it's coming from there. And I didn't have to understand any code at all. I just know that the user controlled the value that I'm interested in, and that ended up in a crash. And that's actually something that will happen a lot in Reven, controlling a value that like that. Again, because this value is just modified and used, but if it was influencing the control flow and that control flow was causing a crash, that's not something you would be able to see using the tainting engine, at least not as obviously as here, but it would still point you to the right location that you need to analyze using usual static analysis tools. And then you might have seen that, yeah, the other results end up in A to I, doing some char conversion, everything. And if you taint actually the result value of A to I forward this time, so tainting here RAX from here and this time forward, so up to the end of the trace, like that, you will see that flags get tainted here, flag C, flag P, flag A. That's because I do a comparison on that value. And that's actually a nice way to find where that value is checked. So obviously, values influence flags all the time, so it's not a guarantee that there's something interesting going on in that place, but in a big program that helps you narrow down the code location that you need to look at. And finally, in the what is the value? Yeah, I dropped a couple of hints here by executing the program a couple of times before, and that value is a bad value, so I know it's going to guard against that, 16381. So if I search for it using the search here, 16381, I think that's right. I think that's the right one, 16381, all right. And search for it, there are 2 places in the code where I read that value in memory. Okay, so I execute the code, search for that value anywhere in the trace, and just by clicking there, I'll be able to synchronize, and this is where I read that value from somewhere. So that, again, helps me find the location of code, which I might be interested in. You know, if I have a crypto constant or whatever, it's a very easy, it's something I think is very easy to reason about. So that's a nice thing to have. So I hope by now you have an idea of the kind of thing that timeless analysis brings to the table. It doesn't replace, did I say static analysis? Dynamic analysis, timeless analysis. But it doesn't replace static analysis at all, but it really complements it by you know, giving you straight answers about something that's happening in real execution code, and might provide very strong hints about certain things, whether a value is controlled, if you're trying to determine if something is exploitable, or maybe where that value is created, if you want to find other possible paths that were not taken, other values, if you have obfuscation going on. Yeah, a lot of use cases where having that trace and having tools like that to navigate is just really something that is going to make your analysis much faster. Extracting information with the Python API. This is what we just did. Yeah, you could have also, something I didn't mention, you could just run guard value and print the values you're interested in. And it gives you every time I call guard value on something. As I mentioned in the chat, we won't have time for exercise 2, at least not right now. So we'll see about that in about half an hour. For now, it's time to work on trace number 3. And on that trace, let me actually open it up. This is trace number 3. I'll give you access to that trace. I'll see how you can access it. But basically, this is trace number 3. Okay, I have a question. How fast or slow is the recording? How large are traces files? So we're recording virtual machines running in emulation mode in QEMU. So that's not hypervised that you are used with usual things. It's really emulated on your machine. What you saw in the example I gave when I made a blue screen of the machine and I recorded something, the VM is slower than usual. You may have noticed that, but it's still very usable as a GUI. So the recording process is slower because it's running in emulation mode, but it doesn't slow down as itself. But you need to configure your virtual machine, having that in mind that it's running in emulation mode. So we provide tools to help you with that. And about how large are trace files? Trace files can be anywhere between 5 gigabytes to 300 gigabytes, depending on how long you record. The traces we're looking at are 5 gigabytes because usually you have a basic VM memory dump that takes a set amount of time, a set amount of space that you can't reduce. And then bigger traces, like I have in mind a recording of VLC and exploiting VLC that runs for 30 or 50 seconds in a Windows VM, and there are a lot of accesses because it's a 1 gigabyte file that's being read, and so that badly influences the size of that. And it's about 250 gigabytes on the disk. That's why we need beefy disks once everything is replayed. Because once all the indexes are created, and creating these indexes can take up to a couple of hours. Okay, so back to our trace, the contest. So now this is a real case. All right, I have at the start, I have my program that triggers the crash, and at the end, I have my crash. You won't see the blue screen in the frame buffer in this trace. You would have seen it in exercise 2. I'm sorry, but usually I just stop right when the blue screen starts because I don't need the execution of the blue screen itself. This is just noise that I don't want to keep on my disk. So for those of you familiar enough with the kernel, KEBug check is the symbol that is called, thank you, Skia, is a symbol that is called when you are triggering a blue screen, and it's going to paint the screen blue and everything. So I'll give you a head start on that trace, and then you'll take over. I'll give you access to the trace and the questions, and you can answer all the questions. But first, let's have a look at that. Usually when you have a blue screen, you need to look at the back. You can either look at the arguments like you would in WinDebug would give you, but here it's easier to look at the backtrace. So I'll move up the backtrace and just skip. There's a stack change here, details that you don't care about. And then what's interesting is the fact that there is a general protection fault triggered by proto PTE3 something. A kernel code, which is not buggy in this case, triggers a general protection fault. And that's your entry point in the trace. That's your divide by 0. In this case, it's not a divide by 0. So I'll copy the symbol to the chat so you can use that as an entry point for your trace. You can search for it and use it as an entry point. I didn't mention you can copy paste out of that environment by using the clipboard here. So if I want to copy something on the VM, yeah, it appears here. And if I want to copy something else, I can type it here and then yeah, didn't work because selection overrides. But if I type something here, I can just paste it there. All right. So you might need that if you get the symbol from the chat and want to pass it here. And it's stored in the NTOS kernel.exe. So starting from there, you will have to move your way up and try to understand where the bug is. The bug is not in that code. This is merely a side effect of the bug, because the bug is a buffer overflow somewhere, and memory gets overwritten. Memory that shouldn't be overwritten gets overwritten, so it gets corrupted, and then that code is using the corrupted memory and then crashes. So this is the usual case where your bug is not where your crash is. So how do you find the crash? It's up to you. This is going to be one of the first questions that we'll have. But really, this is your starting point. You don't need to look for bugs here. There's no bug here, but you need to understand what is happening so you can find the source. One last thing that you will need in this trace is you will end up at some point in a big loop. Maybe I can look for memcopy somewhere, but you will end up somewhere in a big loop, and it's not necessarily easy to know how you can get out of that loop. And the trick I can give you for this time is just you'll see all those multiple times the same block being executed. For what you want to achieve, just copy paste the first address of the block, and look for that in the search. In the search, you can select for symbol, binary address. Look for the address there, search. So here I have a single result, but for that loop, you will have, I don't know, maybe 1,000 results. So imagine your result is there. Just click before the result and press next so you can find the first one. And this will be the beginning of your loop. Okay, so remember that you can get out of the loop that way here. This is just the simplest way for you to get out of the loop at that point. And I think hopefully this is all you need. How to answer questions. Yeah, we need to address how you will be able to answer questions for the next 20 minutes. You will need to through the call stack. Yeah, using the call stack will take you out of the call, but you will end at the beginning of the call, but you will be out of the loop, but you don't know exactly where the loop starts. So you could start searching for your address starting from the start of your call. That would be an idea. You can narrow down the search using these fields. But yeah, sorry, I'm trying to be as quick as I can here. All right, so let's have a look at that. Exercise 2. Okay, a few things. Yeah, the contest will end in, I hope we can take a couple of minutes more. I expected you would need at least 20 minutes to work through that. So let's end the contest at 22. And we might not be able to give you the winners yet because it might take a lot of time. Send the answers to Quentin via direct message. We have a kind of a script running on his account. So send him the messages with the proper hashtag that I'm going to paste to Quentin only as a direct message. And don't worry if he doesn't acknowledge the answer. That's going to be, he's going to be busy looking at your results. Okay, trace is available at port 3040. So you haven't changed port yet because you didn't look at the exercise. But basically in the GUI there, you can click on File, Connect, and change the port. It's 1337. You can connect to 13. It's not going to work here because I don't have the trace running on the right port. Let me show you that here. You can File, Connect 1340, just like that, and you are connected to the same trace that I showed you. This is how you would access. This is how you access the trace. And yeah, as I said, start at KI general protection fault. There are the bug is actually a buffer overflow. There is a buffer overflow. It's not the actual bug, but there is a buffer overflow triggered by some problem in the code. And so don't look for the problem in proto-PT history. And I just pasted all the questions on the chat. So send the proper hashtag, hash Revan Q with a number to answer the proper question to Quentin's direct messages, and we will be able to get your answers that way. And hopefully we'll be able to give the answers, to give the winners, not too late at the end, after the end of the thing. You need to send us your email address because we cannot make a direct connection between an email address and a Discord account. So if you want to enter the contest, please send us the registration email that you used, as well as a direct message using the hashtag #RevenQ0. It will be easier for us to follow what's going on. Did I forget anything? Yeah, do not send multiple answers in a single message. We might miss it. Do not edit your answer. We will miss the edits. So just send a new answer with the same hashtag. We'll take the most recent one. And I think I did not forget anything. If I can just orally give the questions. So the first question is going to be so there's a buffer overflow, and there are a couple of memory. So a whole memory region gets overwritten, but one specifically is then reused by ProtoPT something and that triggers a crash. What is the exact address that triggers ultimately the crash? That's the question one. Question two is where in the trace does this overwrite occurs exactly for that address? So you need to find the exact transition where that address gets overwritten. There are actually a couple of transitions, but at least one of them. That's for the crash analysis, what's happening. And then there's a bug. So you will start analyzing the bug. This is something that you would do usually when looking at a trace. So there's a buffer overflow. I'm just giving you that. But why is the overflow possible at all? What is going on? What makes it possible? Is it because there's an address that's badly calculated? Is it because there's we do a memcopy with too big of a size? Or is it because we allocated too small of a memory region? And that's the three things I can think about that would trigger a buffer overflow. So which is it? And give us a couple of relevant transition, at least one transition number describing the problem that you're talking about. Question 4 is going to be pinpoint the exact transition where there's an arithmetic bug somewhere. Just find it and give us the transition. And Q5 is can you find what value is actually problematic? It's controlled by the user. Just find the transition where the user sets that value up. You can send any question in any order. Each question is 1 point, I think. And in the end, the person with the most points, which reach the highest score the soonest, will be the first, and then in order for the 3 licenses. I hope I was clear enough, and I hope you started looking at that trace. If you have any questions, keep them in the regular chat so that Quentin does not get overloaded with questions. And I'll let you guys work. I forgot to mention the symbol I gave you, KI general protection fault, is stored in NTOS kernel. So I'll paste the proper binary that you need to look for the symbol. If I may give a little hint for those of you who might not have found that yet, just so you can move forward. The general protection fault here is because we are accessing an invalid address. Yeah, you can see it. It's not mapped, so there's no content that we know of. And that address, then it means that address is completely wrong. All right. That is the value that was overwritten at some point. But where is that value coming from? So you need to look at where that value is coming from. It's coming from somewhere in memory as well. You need to find where that value is coming from, and this will give you a start as to how it was overwritten, and you can use then the tools. One of the tools that we saw to find where the write occurred, previous write occurred. So the kind of tools you could use there, if you want to see where this is coming from, you can either use the taint on something there, or you could also use the memory history. And basically, you would do the very start of the taint by yourself using the memory history, and then some static analysis on that. So it's 7 in Paris. So we apparently I slightly overshot the difficulty of the questions I asked. But not having done the exercise mostly didn't help, because most of it was reproducing things we should have done in exercise 2. So if that's okay, we'll give you guys a little bit more time to try to give the answers, to get some answers about the trace. Let's say maybe about 15 minutes more, so that at 15:15 we can stop the contest and see what we have, see the kind of results we have. Again, send the messages to Quentin. He'll help you, maybe guide you a little bit if you're on the right track, to give you a hint as to the kind of things we are awaiting, the kind of answers we are awaiting. And again, a few things have been mentioned. Yeah, using the taint or using the memory history will really help you move away from there, from that call here to some place completely different of the trace where the memory we're talking about gets overwritten. It's quite a buzz, so the contest is now over. Thank you all for participating. We have winners, but I don't know the names yet. We need to manually kind of sort through your questions, and this process is not over yet. Quentin and Kia are 100% into it. So we'll give them some time to just sort through the results. I might not be able to give you all the results too soon. So just know that when we have the result, we'll send them either by mail or through the Discord, or maybe they'll pop up in a couple of minutes, and we'll know about that. Still, we got a few answers. So congrats to all of you for the answers. I know this is probably been pretty rough because when we designed the contest, we had in mind that you would have done exercise number 2, and that would have much helped because you would have manipulated the tool in a real situation before having to do it on your own. So congrats to all of you who managed to find a couple of the first answers. That's pretty cool. I'm super glad that you managed to do that. This is super cool. And I guess we can call the end of the lab. This is way over. I'm hesitant as to whether or not I'll give all the answers for trace 3, because maybe some of you want to keep working on that. Yeah, of course. But yeah, I will give all the answers to that because the contest is over. So let's just have a look at that trace. Okay, let's just have a look at that trace real quick. And then we can switch over to exercise number 2 for those of you who want to keep working. And again, we'll stay a little while longer. For those of you who have to leave soon because we are already way past the time that we had, just thank you. Thanks so much. I hope you enjoyed the lab. I'll send a short message on the chat with a couple of reaction GIFs. I never know. So that you can give us some feedback about the lab, not training, but the lab, what you thought of it, whether it was interesting or not. Of course, you can send direct feedback to me through Twitter, my email, or Discord or Umbrella if you want. But if you don't want to get into that, I'll just send a quick message for the feedback. Let me do that real quick. Okay, there you go. And I'll push a couple of reaction GIFs onto that. Is there a frowning face? Yes, there is. Okay. And all right, just send a frowning face if you want to. Or maybe Skia, can I let you push the first emoticons onto the message so I can head over to the trace if that's okay. Thanks a lot, super. Okay, for those of you who stay, let's have a look at the trace and what this was all about. All right, trace number 3, and then we'll head over to trace number 2. Because this is where the fun stuff is for tonight. Okay, where was I? Here I was. Okay, so that's my general protection fault. All right. That's my general protection fault, and I have an address that's not valid. And what about that address? So RDX is coming from, in this case, let's have a look at it. Sorry, I have some things on the chat. No, that's all right. So RDX is coming from RAX, and RAX is coming from that memory address right here. And that is the memory that is corrupted. Okay, if you double click on it, you see it contains the address I'm interested in, or something close, plus 18 hex. But that's the address that is corrupted, that I'm reusing directly as an address, or mostly directly as an address, and then boom, there's a crash. So I know this address isn't right. And as I told you, there's no bug in that code. It's just that this address has been corrupted before. So I can double click on the operand, open it up here. So this is the current access. We selected by default either the current access if there's one, or the one previous the closest one that's before the transition that you selected. And I see there are a couple of writes here, and those are where this memory has been corrupted. Okay, so just using that, look at that. I'm in conhost something, ring 0, and I double click, and I'm in a completely different process, executing kernel code. I can execute kernel code inside the scope of a certain process. So it's not this exe file executing. It is a driver, but it's coming from a call from that file here. And I'm in a completely different place and in something that looks like a loop, which basically, if you look at it, it writes 6 bytes, 6 bytes per 6 bytes, and that's exactly the transition where the corruption occurs. So there are 4 transitions because I'm writing an 8-byte value. 2 bytes by 2 bytes. And yeah, this is where my corruption occurs. Okay, and if you look at it, you'll see the values on the right get overwritten one by one. You see, you overwrite things. We overwrite things, okay? Yeah, blah, 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 blah. So you see the overwriting occurring here. And the exact transition we were expecting were these. Now, as I told you, there's a loop here, and it's not always obvious how to exit. So the simplest way here is just looking for that address right there, search for it. There are a couple of results. I make sure I'm right before the first one and click on next. And that's the first occurrence of my loop here, of my block. And if you look at it, so that's the address that is corrupted right here, 3B0A20. Let me push that down so I can see the registers. And if you look at it, so if you look at the address 3B something, I think I have, 3A something. So if you look at RCX or RAX, they seem to point at the same buffer. Okay, and I'll give you the answers because at that point you need to be doing some static analysis and look at the code, basically, not necessarily with a static tool like IDA or whatever, but just looking at the code and trying to figure out what it does. And actually, I was writing through RCX earlier, so RCX is the pointer that is containing the current address. Moving back to the exact crash, to the exact transition that caused the crash, you see that RCX. Look at RCX here. You'll see it go. Yeah, it increments 32, 34, 36, 38. So that contains the current address that I'm going to overwrite. And if I go back to the start of the loop, this is the start of the buffer that I'm going to overwrite. You would also see that this is my size that I'm going to write. And since I'm writing 6 bytes for each iteration, I actually write 6 times that. Okay, so I'm writing to a buffer and I'm expecting that to be 6 times that size. And looking at where RBP is coming from, so let's taint RBP, just like that, from there backwards. What did I do wrong? Yeah, I may push something stupid here. It's coming from there. Okay, it's coming from I'm coming from an alloc. I have an allocation right before that. That's interesting. If you look at bcrypt alloc, it actually returns the pointer in RAX, and that is exactly the buffer which I'm overwriting. So the allocation is right here. So that's very easy to look at the allocation. Press %. I go back to the call. I think the size is passed as first argument. So first argument is in RDX, and you can see that I am allocating 2 bytes. So I'm allocating 2 bytes and then writing 2 times 2 AAB. I don't know how much that is in decimal, but that's quite a lot. So I'm completely overwriting that buffer, and I'm allocating a very, very small size. So which is wrong? Is this wrong? Is the size I'm writing it wrong, or is the allocation wrong? And well, if you look at it here, ECX is coming from DI, and then I add DI. And if you look at RDI, yeah, since I'm writing in 16 bits values, I'm completely overflowing here, and that value is overflowed. If you look at it, that's a weird way to multiply by 6. Assume, so at that point, RDX is the size of what I'm trying to write. Then I add it, so that's 2 times my size. RBP contains my size as well. Yeah, RBP contains my size as well. So that's 2 times plus 1, so that's 3 times my value, and then in EDI, and then I add EDI to itself, so that's 3 times 2, so that's 6 times my value, which fits the fact that I was writing 6 bytes per iteration of my loop. All of that you need to look at the assembly code to get. But basically here I'm doing a weird multiplication by 6, and it overflows. And in the end, I have a way too small size. I end up, allocating a very small buffer. So my size seems to be pretty right, and it's pretty well. That's a very, very strong hint that that size is wrong. At least maybe I shouldn't be in the mem copy as well. I should detect that the value I'm passing is way too big for considering what I expected and just exit the loop earlier. Okay, that's probably what I should do if I were to patch that. So detect that there is going to be an overflow at that point, or make computation not using 16 bits value. And again, so we had tainted our thing earlier, and I think I can do the same here. If it's pretty much the same if I taint RDI. I will end up right here. So I didn't look at the results. I just went all the way back to the taint. I didn't look at the intermediary results, and I land in my program, and it's loading to AAB directly, has a hard-coded value into some place in memory. And then after that, there's a mem copy, another mem copy, whatever. And then it's going device IO control, which is talking to a driver, probably with the buffer that it was forming earlier when it wrote to AAB. And you can check that it's actually the case. So right there, I know that this size is totally controlled by the user. And this is where my proof of concept was writing it into a buffer that it passed to a message to the driver cng.sys that will end up crashing the system. So again, many things that you can see with the timeless analysis, and then you need some static analysis to understand what is going on. But here again, we can just make a very quick link to prove that this was completely controlled by the user. And starting from there, you can do the same thing. Taint forward, look at the flags, look where this value is checked, and you can also look at the patched version because it was patched last week. I think this is actually CV 17.0 something. Maybe I'll have a look at the actual number later so I can paste it to you. But this is yeah, actually I do have it somewhere. Yeah, this is 17.087. 17087. This is the CVE number, and it was patched last week, something like that. And the way they patched it was by actually here, instead of here, instead of doing this arithmetic by hand, they called a function which does that safely and returns an error when there's an overflow. So there's that. Yeah, thanks. All right, so that's it for this trace number 3. If you have questions, yeah, please come back to the chat if you have questions. I see we still have 23 participants, so I will keep talking about exercise 2, if you're okay with that. And yeah, I'll keep going, and you can have a look at exercise 2. 30 minutes might be a little small, but I think we'll be able to see quite a few things as well, which I really hoped I could bring you with, because this is, I think, really the epitome of what can be done with static analysis. So about exercise 2, I'll just give you the technical details, and if you have questions, do put them to the chat so I can answer them about trace 3. But exercise 2 is on port 1338 and 1339, but look at 1338 first. So file connect 1338, that, and this is going to be your trace. And Okay, and what do we have? So that's our trace, and you have another notebook here that you can use to in the lab notebooks. You have the CVE, something that you can use as a guided exercise, and this is much more guided than trace 3. So you should be able to just follow it and yeah, and just go on with it. And yeah, again, as to everybody who needs to just get out of the lab, thanks so much for participating in this lab. It was a pleasure to be your host today. And I really hope you can keep in touch. Don't hesitate to send me an email, tweet, whatever. And yeah, I hope we can keep in touch. You know, if you have an idea or something we can work on, you know, reach out. Okay, exercise 2. So this time we do have a blue screen, an actual blue screen, although I didn't keep the recording up until the absolute end because that's a lot of instruction and I really don't want all of that. But still we have some of it. It looks like a blue screen is being built. And actually, so I just clicked towards the end of the trace there and that was my blue screen. And as I told you earlier, you still have the KE bug check somewhere. So here it is. And there is just, you know, displaying the bug check screen, displaying blue screen. It's clearing the screen as blue and drawing rectangles and drawing pixels and whatever. And if you look at the frame buffer, so I'm zooming with control mouse, which is the usual thing. I think we should be able to see the lines being drawn. Did you see that? Did you see that? Look at that line. Look at that line. It's being copied over block by block by the mem copy. It's completely useless, but I think it's absolutely, I think it's awesome to see that. You know, you do see everything when you have a full system trace, even though there it's completely, you know, just for fun. But I think it's a pretty interesting thing. Still, what we have is a KE bug check, and we need to have an idea of what is happening here. And in this case, it's so the KE bug check is called by somebody, and the someone is the raise security check failure. So in this case, the crash is just very close to where the bug is. For those of you not familiar with security checks, security cookies, sorry, it's just a value that is hard to predict, that is pushed on the stack at the very beginning of a function, during the prologue of a function. So if you do overwrite something on the stack and you go and you write way past what the function is allowed to, this check is going to be overwritten as well. And when you exit the function, before returning from the function, you check that your cookie is still valid. And if it's not, then you raise an exception. And here, since the code doing that is a driver, it's not just an exception. It's just a blue screen because of the security problem with the driver. It's a pretty big deal. So what we have here is our security check cookie. And so I jumped there and raised the security failure. And I see there's a comparison. So that's where I compare the cookie I just read with the value that I'm supposed to have here after absorbing it in some way. And the place I read it is right here. This is where I read. So you see RBP is, you know, here in this case, it's on the stack. You can check the RSP to make sure of that. So I read that value here, place it in RCX, do a little something XOR, and then compare that value that was supposedly hard to predict to the hard-coded value that I know it should be. And if it's not, boom, I exit and I raise a failure. So at that point on, I hope people are still following what I'm saying. That value was overwritten. And as we did before, looking at the memory history, we see the write here, and the previous write is the one that wrote that value. So this is where the value was overwritten. Okay, pretty similar to what we did in trace 3. This is what doing that after trace 3 would have, you know, probably been a better way of doing this. I'm inside a mem copy. Just as before, I have a couple of blocks that are going to write that thing. But this time it's just not just a loop, it's an actual mem copy call, so I can move to the start of the call and see what I'm doing. I'm going to assume there's no bug in mem copy itself. So my assumption is going to start at, is there a bug in NG's get data buffer? And I think that's where the exercise starts. So for those of you interested, you can head over to the notebook and start looking at the bug, and it's going to, you know, do a couple of things. I'll leave you guys about 15 minutes and then we will wrap up. So go as far as you can. And in 15 minutes, we will stop and I'll wrap up the exercise, just give you the answers I wanted you to see, because I think the end result is pretty interesting. But you know, that's my opinion. And then we'll wrap it up for real. So go ahead, run wild for 15 minutes. All right, guys, we're reaching the end of the lab this time. It's 10 to 24, to 23, sorry. So we do have our winners available. Let me pass that to the chat. I removed the ads. Let me push the ads so that we can have the proper handles. Okay, so CHQ Matteo won the first place with a 12-month license, then Nitron, and then Man Obit with a third place and 3 months license. So congrats to all of you. That's so cool. You guys managed to dig into that tool. That's not an easy thing to do when you're not familiar with timeless analysis. And so congrats to 3 of them, and congrats to all of you for participating. This is really cool. I'm so stoked that you guys, took it from zero and then managed to actually use that and start solving a real problem with it. This is in just a span of less than 2 hours. This is really cool. So I love that. I gave you all the answers already for that, but let's just take 5 minutes to have a look at this exercise too. I'll just throw the things at you before we part. So yeah, the exercise will make you follow. So the bug is not here. The bug is actually in IPv6 handle router advertisements. And if you look at, I think, let me think. Ooh, where's my CPU view? I don't have registers. Show me the registers. So that's, this size is way too big, basically. This size is way too big. So you would take that backward and find, let's do that. Let's take that backward, RDX, from there to the first transition, like so. And yeah. And if we turn that backwards all the way back, we end up in net.io.sys, and that's actually the code reading the packets from the network. And if you look at the CV, the pcap file that we extracted from the trace, the data is actually stored right here. This is the 22. This byte 22 ends up being 110. So it's been multiplied by something. And then we use this size, and this size is wrong. Okay. So what you can analyze here is actually not the bug, but the setup of the bug. The setup of the exploit, sorry, setup of the exploit. So there's a bug which triggers an unexpected code path, and then the exploit, or here proof of concept, leverages that new code path to set up something so that it crashes. So what we can see here is the setup for the crash. That's not actually the bug. You need to dig a little bit more into that using by analyzing the code around and get more information. And what you would see if you did that, you would see that basically this data here is not meant to be read as a packet. What you have here are not packet, but really options, basically data structures that are read, all right? Data structures, and we parse the structures. And that is, and the structure is just a type size value. And so what you have here is the type, then the size, then the value. And that's not meant to be its own option. This is supposed to be the start of the option, and this is supposed to be part of the option, all right? And actually the problem lies with that packet here. And what we're going to do, and that really is what I wanted to bring you guys up to, was we can look at the patch that they did to fix this issue and understand what the problem is and how they patched it, both at the same time. And that's what we do with the exercise. If you look down, towards the end, I explain everything I said. So what you would do here, the approach we can take is taint, let me look at that. Taint those bytes forward, starting from the beginning of my problematic function, and see how it's handled, and taint that both in my trace that crashes and in my trace that doesn't crash because it's fixed. And by looking at the differences, I'll be able to pinpoint exactly what the problem is. I could diff instruction by instruction, the two functions, but there might be many differences between the two, especially in this case, because the two versions are pretty far apart. But also I would have unrelated changes or address changes, which are not actual changes, but still, differences, or maybe the compiler uses a different option or whatever. But by looking at just the code that manipulates my first byte and then my second byte and then my third byte, I will have a much reduced perimeter. And so the taint here is going to help me reduce the perimeter and look at things in a way that makes more sense. So that's what we do in the exercise later on. So I just taint the first byte. It's offset 10 in the packet. As you can see here, it's offset 10. So I taint that first. This is the type of the time length value, TLV. Yeah, that's the word. And you can see that there aren't too many differences at first, and then we somehow prematurely exit the function, which makes sense because we patched it and there's a problem with the value, so we just exit the function. So I don't see much differences here. But then if you look at the second byte, which is the size, and execute that again, I did the thing, then I'm comparing it using, so this function does the comparison, and I'm doing that using standard Python tool, nothing fancy here under the hood. And what we have here is much more interesting. I see that some piece of code was inserted, and what it does is so if you look at the value here, what do we have? We have my value going from 4, that's my size, to 20. It's shifted left 3 times, so it means it's multiplied by 8. So 20 is my size multiplied by 8, and then I take away 8, and then basically I compare it to FF. So I compare the lower bytes after having taken something. So you could disassemble that or just take some time to think it through. That's just actually checking the oddness of 4. Checking the oddness of 4 by checking it. Is it a multiple of 16 or not, which is 2 times 8, 2 times the time I multiplied my value from. So I'm actually checking the oddness or evenness of that value. And and here I'm in a case where I just exit the value. So that's what the patch did right here. And I can actually click on I'm not listing because I didn't synchronize. But just clicking here, you will see that code right there. Test right there. I see the test, and I take the jump here. I don't take the jump because my value isn't what I expected it to be, and then I prematurely exit the function instead of doing all the problematic copy that would end up in a crash. And if you look at the end of that trace, there is no crash. So I thought, this is the thing I wanted to show because it's really leveraging this kind of information to, again, narrow down the scope of what we're trying to do to provide something that makes as much sense as possible. And that's it for this lab. This time I can proudly show that for real. Thank you, everyone, for following this lab. Thank you for staying up one more hour for the 16 of you or so who just stayed up an hour more. I really appreciate it. I hope you learned something. Don't hesitate to reach out. And again, if you haven't yet, just click on the icon to give us a feedback. And again, congratulations to the 3 winners of the contest.